So again, in this lectures, we are going to discuss about unsupervised learning algorithm. As we said earlier, the beginning of the semester, in machine learning, we have four different categories of tasks. Our textbook covered three categories, which is supervised learning, unsupervised learning, then reinforcement learning. So today is our first lectures for unsupervised learning. So let's see our main objective. So our main objective today is to go through the concept of unsupervised learning. So what is unsupervised learning? Why unsupervised learning? I'm going to answer this question very quick. Why unsupervised learning? Because we don't have training data. Or the data we have, we don't have the target variable. So our last option now. Sometimes we can have a data and we are assuming that the data is not a training data, but it's a training data. But the goal is that we want to group the data into three or four, in any amount of groups based on some similarity. So sometimes we can do unsupervised learning to reduce our data. Then we focus on a specific task that we want to do. And this time we are going to use supervised learning. So we have three types of unsupervised learning. Cross-story is the most common one. We find data that are similar based on distance measurement. If they are similar, they will be grouped together as a one cluster. If they are dissimilar, they will be in different clusters. Then, yeah, that's what we are saying earlier. We can use unsupervised learning as a dimensional reduction also. So the goal is to reduce the dimension. Also here, that's why we wrote briefly. Association rules sometimes can be used as a supervised, and sometimes we can use it as a unsupervised. Yeah. Then in this lecture, we're going to find the ways we can evaluate unsupervised models. Then we'll look at some examples, applications, and where we can use unsupervised learning concept. So let's start with the definition. What is unsupervised learning? I would say that unsupervised learning is first of all, it's a subfield of machine learning, which concern with finding patterns. We are looking for patterns in the data that has not been explicitly labeled or classified. So here we are not using the training data as we went through supervised learning. So I would say that unlike supervised learning, where the model learns from output pairs, unsupervised learning algorithms are given only one input data, and the task with discovering what? Some hidden patterns or discovery inherit structures or relationships, or we can even say discovery distributions. Yeah. So that is what we call unsupervised learning. So here we are not using the training data. So the goal, as we said earlier, that's the goal also, to find the hidden patterns, structures, relationship within the data without explicit guidance. You know, with training data, we have the target variable. That's our, or class level. That's our guide. That's why we say supervised learning, teaching, like leadiness. So that's an analogy we have. So imagine being given a large collection of photos, but these photos without any captions or categories. There's no any categories. Unsupervised learning I would say would be like trying to group these photos based on their visual similarities. So for example, we may group photos of a tiger or photos of any animal together, the same animal together. Or we may group photos of, let's say we have photos of animals, people, table, objects. So here we may be able to group all the photos of animals as one cluster, all the photos of a table, different tables or something as one cluster. So that's the whole goal. Or finding the common object within them without ever being told that this is an animal or this is a table. We are or a landscape or something. We don't know. So that's the main. Uh, Comparing with supervised learning, as we said earlier, we learn from label, input, output. Example, classification, regression. We went through the concept already. So unsupervised learning learn patterns or structures from unlabeled data. The data has no target variable, nothing. So that's all we can say here, the difference between the two, supervised and unsupervised learning. And as we mentioned earlier also is that sometimes we may have a training data, but we can use unsupervised to find some pattern. So unsupervised learning, we are assuming the training data doesn't have no target. But the reason why we want to, I would say data segmentation, data set segment. We want to divide the data maybe into two, three, any amount based on some criteria. That criteria will be the similarity. Yeah. Let's wait for a few seconds. Again, as we said, always, if you have a question at any time you speak, I'll just keep quiet, listen to you. No, I shouldn't say keep quiet. If you have a question, I'll just, yeah, keep quiet, listen to you. Yeah. So let's see if any question. If no question, let's keep going. So here they say, why unsupervised learning? I think we already explained some of it already. First of all, here they say the data library is expensive, or it seems even sometimes it's impossible. So we don't have no training data. So if that is the case, yeah, unsupervised can work. Or as we say, we can also use the EDA. We are trying to gain some insight or understand the underlying structure of data. So manually labeling large data sets. Here we are talking about machine. I mean, a large data set. If not in millions, it's in thousands. It will be very expensive. Not only expensive, it will consume time, costly and time consuming. So again, manually labeling large data set is often it's impossible. Actually, I won't say costly. It's also impossible in terms of the time, effort, and also financial resources. Yeah. So the next will be the feature engineering. Here we say discovering new features for supervised tasks. So that's what we mentioned earlier. Sometimes we may decided to use unsupervised learning first. The goal is to reduce the data, if not the data, the feature, reduce it. Then from there, we move on to supervised learning tasks. So exploratory data analysis, unsupervised techniques are excellent for initial data exploration because they help review the inherit grouping or identify. Actually, with unsupervised learning, we can also identify outlines very good. Outlines and also understand the underlying data, or I would say the distribution of the data, understand the underlying distribution of the data, which can then inform maybe further analysis. In this case, maybe choose some supervised learning algorithm or even move to the feature engineering concept. Now, with feature engineering, here I would say that the output of an unsupervised model, for example, cluster assignment, or even reduce dimension, the output can be used as a new features for subsequent supervised learning tasks, as we mentioned earlier. Potentially, the goal is to improve the model performance, Also, in terms of anomaly detection, yeah, unsupervised can work. So deviation from learn normal patterns can be identified as abnormally or as outliers. If we are deviating from something which is normal, then it becomes abnormal. So here the goal is to identify unusual data points. So again, unsupervised learning can be used for anomaly detection also. Yes, don't get me wrong. Also, anomaly detection can be used by supervised learning also. That's if we have the training data. A very simple example, I use a credit card in New York City always. Hardly before I spend more than $200. So what the credit card system, they got my profile. So Chasedeki, for the past 10 years, credit card only New York City. All the items less than 200 profile. All of a sudden, I end up in a vacation place, maybe in Jamaica, England, Europe, and I'm buying one item for $10,000. Most likely there will be a flag. There will be a flag. And this is anomaly detection because unusual usage of my card in different country, and the amount is way too much. So this will be supervised learning. Why? Because they have my training. They build my model. Should I say model? They build my. That's a recommendation. That's a term that we use. So no, based on that, they can, yeah. Now the next will be data compression. Also can be used and unsupervised learning to reduce data size while retaining again information. So, example, reducing the dimensionality of data can lead to what? A more efficient storage. Not only efficient storage, but computation. We all remember we use the term dimensional case. High dimension data so we have high dimension data is not really too good. Now, I mean, it's good, but algorithm may take too long. And also sometimes you have two attributes that almost have the same information, date of birth and the age. So this is the work of PCA and singular value decomposition, which hopefully we will discuss that. Then lastly, I would say the pre-processing step here also. So we can start with unsupervised first before we move on to supervised learning, as we said earlier. So what are the types of unsupervised learning? Here we have cross-story. Cross-story means grouping similar data points into clusters. So if they are almost similar, they will be in the same cluster. If they are dissimilar, they will be in different clusters. So the goal of clustering is to group a set of data objects into subset clusters, such that the objects within the same cluster are more similar to each other than those in other clusters. Most of the time in these lectures and also our textbook, how do we determine the similarity of the data so that they will be in the same clusters or different? It's based on this distance measurement. Our textbook, I remember, they discuss about Euclidean distance is the most simple distance. Almost every textbook talk about. So Euclidean distance, we have Manhattan distance, whether Minkowski or Minkowski distance. Again, we will go through them. But measuring in cross-storing to measure similarity, we use distance measurement. That's what I want us to know here. So, what, for example, let's say what would be a key question here? What data points are naturally similar or belong together? So, again, we can have some application here like customer segmentation. Customer segmentation means we are going to group customers based on the profit we are making from them or based on their purchasing power. So, or purchasing habit, I shouldn't say power. Well, this is so customers that are more profitable, or based on different items they buy, we group them. Another would be social network analysis. Social network analysis, here we can identify different communities. Documents organization, I think we do a lot of that. We can maybe based on the content of the document, we can say whether it's politics or it's sports, etc. And the most popular is also image segmentation also. It's very common, image segmentation. Also, we use this a lot in the bioinformatics, computational biology for gene expression. So we can use clustering for gene expression in the sense that if two genes have the same expression level, most likely they are doing the same function. So we just put them together in one cluster. Different expression level will be in different clusters. So let's wait for a few seconds if everything is okay. Okay, so let's keep going. So we talk about also association. We talk about, again, association rule concept. So, for example, discovering relationship between variables and also variables in a large data set, etc. So, for example, actually, we discussed about the market basket analysis. What is the chance that if I buy bread, I will also buy beer or peanut butter? And normally, we are going to use the concept of confidence and support to measure the strength of the rule. or it's called implication rule, if then rules. Again, in general, it works in clustering. Actually, also neural networking, we have, as we said earlier, we have a special neural network, which we call the self-organizing map. It's a clustering concept. It's a neural network clustering algorithm or supervised. Yeah. So let's deep dive about clustering again. As we said earlier, the main objective to partition data set into groups, clusters. Similar data will be in the same cluster. The similar data will be in different clusters. So that's what they say. Data points within the same cluster are highly similar. Data points in different clusters are highly dissimilar. So the key challenge is defining the similarity, which, as we said earlier, is about distance metrics. So the common distance measurement, as we said earlier, was Euclidean distance is good, Manhattan distance. Then we have Minkowski, so many of them. So one of the first algorithm we are going to discuss, again, here we're just summarizing things up, is the K-means. We are going to go through K-means. Then now K-means also have as we all know, even let's go back to statistics. We know in statistics, mean, the value of mean is very prompt to outline data set. If a data is very small and the data is very big, that can change the mean value automatically. So the same concept here also. Because K-means is prompt to outline data, we solve that problem having another algorithm called the K-median, MEDIOD, mediod. And that one it doesn't based on the mean value, it's based on the position of the data points. So it's more robust to outline data. Yeah, so let's look at the concept of K-means. And that's one of the, even our textbook mentioned K. So as we said, unsupervised learning, there are so many algorithms. We will mention a lot of them, even these slides we will mention them, but we can't go detail all of them, again, because of time. Yeah. But K means we will go more detail. That's the test. Again, we're trying to cover what the textbook cover. Not to go to. Actually, if we have time, we can go far. But let's see if we have time. So let's go straight. As we said earlier, the concept of K-means, we use something called the centroid. So it's a centroid, so that's the first thing here, a central base algorithm. And this central base algorithm is to aim to partition, let's say, n observations into K clusters. So the term K means the number of clusters we are going to have, the number of clusters. That's also another challenge. What to be the best number of K we should use. This is a challenge also. We'll discuss about that. So again, first we have to know the number of K. And also because we are going to partition the data set into K clusters. Now, each observation belongs to the cluster with the nearest mean. The nearest mean, we'll use the term centroid. Centroid, serving as the, I would say as a, I'll use the term prototype, serving as a prototype of the cluster. Yeah. So that's the whole concept here. And here we can see the algorithm. So as we said, the first thing we have to do is to initialize. That's choose the number of clusters you want, which will be the K value. Then we randomly select the K data points from the data set to be the initial centroid. Again, the term centroid means the cluster centers, the cluster centers, the center centers. Then next, now we assign, that will be there. So we finish with the initialization step. The assignment step, what we do is that we are going to assign each data point to the cluster whose centroid is very close, or I would say whose centroid is closest. Now the closest will be based on the chosen distance metric. Let's say typically we're going to use Euclidean or Manhattan distance, depends. So after that, now we have to do updating. So we update step, which means always we are going to recalculate the centroid by taking the mean of all data points assigned to that cluster. Then the convergency. we will repeat step 2 and 3 until the centroids no longer change significantly. That's converging or convergency. Yeah. Yeah. So when it doesn't change no more, that's it. Or another option, a maximum number of iteration is reached. Kind of idea of like neural network, the number of epoch. So if the number of iteration we specify reach to stop, or we just let it go until the value doesn't change no more, and the central no longer change, then we stop. So I would say that's the whole idea. We'll finish with the algorithm. So yeah, they give, oh, let me wait for a few seconds. So actually in the slides here, we have initialize, assign, update, repeat 2 and 3 until no longer changing of the central or until we reach the number of iteration we specified. Most important thing also, which will be one of the key challenge, is K. So here we have to start with the number of K, a number of clusters we need. So this will take us to some algorithm whereby we don't choose the number of clusters. The algorithm will do everything for it, but we'll see. Let's finish with this first, if any question. Okay, so it seems like there's no question. So let's go through some of the advantages and disadvantages. So we can see right there. First of all, we know the goal. The goal is again, here will be, I would say, to reduce the number of random variables, which to be or features or the attribute under consideration by obtaining. Again, first of all, let's go through this. So one of the pros here, as we said earlier, simple, fast, works well for spherical clusters. Also required, yeah. So that's would be so. As we said earlier, we always have to know the number of clusters we need. So this will be one of the issue, if everybody agree. And also it's very sensitive. So this is what we mean by the outline data. Sensitive to initial centroid and also struggle with non-spherical vary distances, etc. Yeah. Let's wait for a few seconds. Again, we'll go detail on this later on. We'll see some example, but not on this slide. This slide, we just want to summarize everything. Okay. So choosing the right key, that's the main issue. We have so many methods here that we can use. And one of them is called the elbow method. So elbow method is kind of a plot. So we are going to plot the within cluster sum of square. That's the WCSS against the different values of K. So we use different values of K. Then WCSS measures the sum of square distance between each point and also the assigned centroid. So we see as K increases, most likely the WCSS will always decrease. It's always decrease. That's how the algorithm works. It always decrease. Then the elbow point on the graph where the rate of decrease significantly slows down. It will significantly slows down. This is where we are going to consider a good estimate for the K. That will be the good estimate for the K. So as the K again increases, the WCSS will always again decrease. So we look for the elbow point where the decrease in WCS slows down. And that will be the good K to take. Then we have another method called the Sihote score. So for, I would say that for each data point, we calculate the Sihote coefficient, which measures how similar it is to its own cluster comparing to other clusters. Then the score range, normally this score ranges from -1 to +1. Now, -1 means it's a bad clustering. Normally, we don't get one perfect one, but if you get plus one, it means perfect. So it will be somewhere between, let's say, zero point 0.5 to close to, then is good. But positive one means, again, perfect clustering. So the higher average SOAT score will indicate better defined clusters. That's the main thing here. Then we also have the domain knowledge. Yeah, I would say often the most practical approach. So business understanding can lead us or can guide us to a choice of good care. This is again domain. Maybe if engineering, computational, if I know my domain well, I'm doing, let's say, gene expression clustering. If I know my field very well, then I can determine. Yeah, I've been doing this for many years, or let's say couple of times. So it's easier to determine. So yeah, there's no any techniques based on experience or your knowledge, your domain knowledge. You can come up with the best one. Visualization again also go with the elbow method. So we can have the elbow method graph or the COT score concept. Yeah. Let's wait for a few seconds. Hopefully I'm speaking. I try to speak louder as much as I can. So hopefully everybody can hear me. Again, as usual, if you have any question at any time, you can stop me. I mean, not stop me. You can speak then I'll listen. If no question, let's keep going. So we finish, as I said, we'll go details on the K means and K method if time permits. Here, just to summarize some of the concepts here. So the next one we are going to discuss now will be the hierarchy or hierarchical clustering. So the concept again, as we said here, is to build hierarchy of clusters. Now we have two types of hierarchy clusters, agglomerative and also divisive. Agglomerative is bottom up, divisive is top down. Yeah. So with a agglomerative, we can say that we normally go into, so one, we're assuming all the data set is one cluster. Then we start to break it down. The other will say, okay, each is a cluster, then we start to build it up. So that's why it's hierarchy kind of form. So with the agglomerative, bottom up means what? We start with each data point as its own individual cluster. So with agglomerative, even if we have 100 data set, each data is a cluster by itself. Then from there, we build it up. So interactively, we are going to merge, let's say, two clusters or the two closest clusters until only one large cluster remains. Or if we have any stopping criteria, we stop. So that's the whole concept of agglomerative. That's why it's called bottom up. So we go from down. Each data is a cluster. Then we build them. The closest one become two clusters, three, until we reach the top. Now, divisive then will be opposite. That's why we say top down. So with divisive, and define how the distance, also it will define how the distance or similarity between two clusters is calculated when we are merging. So here we say what? Start with all data points in one cluster. So opposite. Agglomerative, each data point is a cluster. We start with that. Divisive, we assuming all the data sets, start with all the data sets in one cluster. Then recursively, we start to spread them into smaller clusters. Again, based on some criteria. Based on some criteria. And here also we use something, so this is using what we call the linkage methods, agglomerative. So let's move to the next. Let me wait a few seconds if any question. Okay, so let's see the first agglomerative linkage method. For example, we have here we didn't mention, yeah, right here. So we have single link, complete link, average link. How we calculate the distances is slightly different between all the three. So with single linkage, we normally call it the mean. So that's the distance between what? the closest pair of points in two clusters. And then it will tend to form a long, they use the term stragger again, clusters. The shape, straggle clusters or something. Then complete linkage is what we call the mass. So that's also distance between the farthest pair of points in two clusters. Then this one normally will tend to form more compact clusters. See, the single linkage is called mean. Why is called mean? Because it will define how clusters or similarity between, uh, uh, the single linkage, we find the closest, the distance. So distance between the closest, so the distance will be, I will say, well, let me use the term minimal. Then because the closest, so again, single linkage. So that's why we call it mean, MIN, minimal, let's say, because the closest, if they are close, distance is small. But with the complete, it's called mass because the distance will be two data points that the distance far away. Or in terms of, based on the slide, they say distance between the farthest pair of points in the two clusters. In two clusters, tend to form more. Then we have the average one, also average link. So the key term here is average. So this will be average distance between all pairs of points in the two clusters. Then we have one more method, which is, they didn't mention here, which we call the walls. The walls method. Normally it merges, so it will merge clusters to minimize the variance within, again, each cluster. This is often preferable. It's preferable for, I would say, for general purpose clustering. Yeah, general purpose clustering. So the next one will be the dendrogram. Again, as I said earlier, we will go detail about some of them, but yeah, just to get the idea. So dendrogram normally, the term is given to us. It's like a tree-like diagram, a tree structure. I mean, TREE, not tree, pronunciation. Tree-like structure or diagram that record a sequence of merges or splits to record it again. So normally the y-axis will represent the distance, or I would say dissimilarity at which clusters are merged. Yeah, something like that. Now, to obtain a specific number of clusters, we can cut the dendrogram horizontally at a certain distance level. It's up to us. So here we say cutting the dendrogram at certain height will yield a specific number of clusters for us. So let's wait for a few seconds. If no question, then all this we talk about, let's see the pros and cons. Yeah, first, all this, no need to pre-specify the K. So that's good. So with higher ranking clustering, the K challenge is eliminated. So we don't need to specify beginning. Then, as we can say, agglomerative means beginning, we assuming all the data points, each point is what? It's a cluster. With divisive top down, we are assuming what? All the data points is one cluster. Then we start to break it. Agglomerative, we start to combine or merge from one. Yeah. So K problem is solved. And also we can visual the dendrogram. So visual the dendrogram provides the insight also. Let's wait for a few seconds. Hopefully after these slides, there's one slide in the class. I think there's a diagram on the concept they are discussing here. We can take a look at the diagram if we need to. Okay, so it seems like there's no question. So let's see the cons. Computationally, yeah, we say it's computationally, again, intensive. Computationally intensive. for large data sets, and also can be very sensitive to, that's what we don't want, and very sensitive to noisy and outlines also. So as we said earlier, no need to specify or no need to pre-specify the key. Also, one thing also, you can review the natural grouping at different levels of I will use the term granularity, different level. We can see the visualization at each step. Okay, so now computational intensive, or I would say expensive even, with this concept, we may get somewhere around big O n cube. It depends. It can be up to a very exponential n cube. So, especially for large data sets, or we may get big O n square log n. It will be more than n square, but according to most of our sources, textbook also. Okay, so if no question, let's move on. Okay, so that's the concept. The next concept is the DB scan also. This is the density-based one. First of all, let's look at our time. If we need to take a short break here. Oh, it's past 1 hour. Okay, so what we're going to do, I'm going to pause the recording. We already passed 1 hour. So, okay. Okay, so we're talking about the DB scan. Again, DB scan is the density base, or in short, density based spatial clustering of application with noise. So if no question with our previous lectures, let's go straight to it. So the concept here again is first of all, it's a density based algorithm. And the goal is to again group together points that are closely packed together. So the more dense place will be one cluster together. Yeah. Actually, hold on 1 second. Let me do this. Let's pause it 1 second. Yeah. So again, the density base. Everything is based on density. So a density-based algorithm, as we said earlier, groups together points that are what? Close together, or they are all packed together. So more density area become one cluster. Then if there's a less dense density between them, then that will separate the two clusters. Yeah. So this marking, well, one thing we can say here also, this is very good when it comes, actually that's what we are saying here. Group together points that are closely packed, marking as outlier points that lie in a very low density region. So it's very easy to identify outlying points. Normally they will be way out where they are way less density. Now, in this concept, we have some few parameters that we have to consider. So the key parameters are only two of them. Epsilon, or how they call it, epsilon. So epsilon will be the maximum distance between the two samples for one to be considered as in the neighborhood of the other. So maximum distance between two samples for one to be considered as in the neighborhood of the other. So normally this will define, I would say to define the radius of the neighborhood around a point. Yeah, that's a good way to say it. And the second parameter is the mean samples. This will tell us the minimum number of points, including the point itself, required in an X neighborhood for a point again to be considered a core point. So those are the two again key parameters for density base. So we have what we call the point types. So the core point will be a point that has at least the minimal sample points, including itself, within its F's radius, the F's radius. Then we have a border point. A border point will be a point that is within F's distance of a core point, but it's not a core point itself. It's not a core point itself. And I would say that is it has a fewer than the main sample point in its own F's neighborhood. In its own F's neighborhood. Let's wait for a few seconds. Normally, this is where sometimes students ask questions. So let's see if the concept is okay here. So again, we have some pros and cons. As usual, nothing is perfect in life. In universe, there's nothing perfect. So we have the pros here, and also we have the cons. So we can find arbitrary shape clusters. Also, it's very robust to outline, easily to identify outlines since it's density. And also, as usual, doesn't require the number of clusters we need. Cons will be we struggle with different or varying densities, the different densities. And also, it's very sensitive to the two key parameters, the F's and the mean samples also. Wait for a few seconds if it's okay. Okay, so if no question, I think that's it. As we said earlier, the cons are also difficult in handling the clusters with, again, different densities or varying densities. As we mentioned, also sensitive to parameter choice. Here we talk about the F's and the mean sample, the key parameters. Okay, so let's see the next concept. So as we said earlier, we can use clusters also as or unsupervised learning as a dimensional reduction techniques. So as we all know, dimension reduction algorithm, the main idea is to transform a high dimensional data into a lower dimensional representation. And the main key, it has to preserve as much of the relevant information or variances as possible. We are reducing the dimension, but we still want to preserve, or we want to have the knowledge still available, or the information still available. So let's see the benefit of, I think the first will be the case of dimensionality. High dimension, we have problem. So the case of dimensionality mitigation, many algorithms perform poorly with high dimensions. Also improve model performance. Can remove the noise and redundancy. Then we also have a faster computation, reducing the training time for subsequent models. Then data storage and also visualization. So with the data storage, we can say that it requires less storage, or I would say less memory. Less memory. So we have two main categories here. Either the feature elimination or feature extraction. So feature elimination, we will say concept of selection. So select a subset of the original features. For example, using feature importance. Or actually, we can also use the correlation analysis for the feature elimination. Then we have the feature extraction, which is a projection. So again, feature elimination is based on selection concept, and feature extraction will be based on projection. So normally to create a new fewer features from a combination or transformation of the original features. And principal component or PCA, principal component analysis is a prime example for this concept. That's for feature extraction. So that will lead us to the concept of principal component analysis. So I would say that it's a linear dimensionality reduction techniques that transform data into a new coordinate system such that, again, the greatest variance by any projection lies on what? On the first coordinate. The first coordinate, again, that's what we call the first principal component. And then the second greatest variance on the second coordinate and so on. So normally these new coordinates we call the principal again component. Now the goal is to find a set of orthogonal or uncorrelated principal components that will capture the most variance in the data. The goal is to capture most variance in the data. So the first few principal components often account for most of the data variabilities, the first few. Let's wait for a few seconds if any question. Other than that, we go through the steps. So the algorithm step, the first thing we need to do is to standardize the data. So this means we have to make sure all the features have a mean of 0 and a standard deviation of 1. Again, this will prevent the features with large scales from dominating the principal components. Then the second option can be to compute the covariance matrix. And normally, this matrix will show the relationship here, the relationship which in this place the covariance between all pairs of the features, the relationship between all pairs of the features. Then that will lead us to the concept of finding the eigenvectors and also the eigenvalue. So we need to find the eigenvector. That is the third step. So first we standardize the data. Then again, we compute the covariance matrix. Then now we calculate the eigenvectors and eigenvalues. Let's wait for a few seconds if, again, everything is okay. Okay, so what is eigenvectors? Again, if you have taken a linear algebra, then we understand the concept. So normally it represents the direction. And these directions is the principal component along which the data varies the most. So where the data varies the most, the direction. So it will represent the direction along which the data varies the most. Then we have the eigenvalues, which normally represent the magnitude of variance again, along the corresponding IG vector. Yeah. So the last thing we can say here is that the higher or the larger the IG value means that its corresponding IG vector capture the most, or I'll use the term more variance, capture more variance, or the most variance, or something like that. So normally the principal component will sort the hygiene vectors. We sort the hygiene vectors by their corresponding hygiene values in descending order. In descending order. So it will choose the top k eigenvectors, where again here the k will be the desired number of dimensions. Then k will represent the dimensions. That again express the sufficient amount of the total variance. Then the last year we have to know to project the data will be the final stage. So here we are going to transform the original data onto the new k-dimensional the subspace that we again define by the selected hygiene vectors. Yeah. So what we are saying is the steps from 1 here to 5. So the next section, we're just going to discuss the pros and cons for PCA. First, we say very difficult to interpret. So loss of interpretability. And that will be the con. Loss of very difficult to interpret. And also it assumes linearity. And that also is the con. So PCA works best when the relationship between the variables are linear. So for nonlinear relationship, we have to use other techniques. And also can lose information. That also is a con. Okay, so let's look at the pros. First, actually, I saw a slide here say effective for reducing noise. I think that's the main goal of a PCA. One of the main goals, effective for reducing noise in data. Also can significantly reduce the number of features. That's another major goal of using. That's the process of the hygiene vectors values. And I think that's one more can lose information. If too few components are chosen, potentially important information like the variance might be discarded or lost. So let's wait for a few seconds if any question. Other than that, let's go. So that's the evaluation of unsupervised model. Yeah, the first thing we can see is it's a challenge. Yeah, there's no any ground truth labels to compare against. So evaluation is a challenge. We may have external evaluation and also internal evaluation. Yeah. So with the internal evaluation, we mentioned the SOAR score. We also have the Davis Bowden Index and inertia. Let's wait for a few seconds if it's okay. Okay. Then we also have the domain expertise and visualization. So for evaluating, crucial for assessing the usefulness of the results. Also within the external evaluation, we have the adjusted run index. which measures similarity between the two clusters. Okay. So what are the application use cases? First, we have customer segmentation or marketing and customer segmentation. The goal here is grouping customers based on purchasing history. Then we also have a recommendation system or recommender system. Here we can identify users with similar preferences or items may have or with similar characteristics to suggest a new product. So customer who buy X, let's say also buy Y or any. Then we also have the anomaly fraud detection. I think we discussed that earlier time. Image compression, also the same with segmentation. Then document clustering and genomics bioinformatics. So again, unsupervised learning can be used in this field of. Okay. So that would be the end. So in summary, as we said earlier, unsupervised learning discover hidden patterns in unlabeled data. So this is not a training data. Clustering will group similar data points. We use K, we saw example of K-means, I-rank, and DB scan. Then also we say clustering can be used as a dimensionality reduction. So let's wait for a few seconds if any question before we end. Okay. So that will be the conclusion of this. So conclusion of this lecture, one last thing we can say, again, unsupervised learning is an indispensable tool in machine learning, especially or particularly when labeled data is very scarce or it's not available or non-existent. So then it empowers us to last thing, uncover hidden structures and patterns in complex data set or perform exploratory data analysis, PCA, etc. Yeah. So let's wait for a few seconds. If no question, then that will be the end of these lectures. We are going to stop the recording.